Metal alkyls. Metal alkyls had evaded chemists for quite a while, with some early success, but then it got stalled. And part of the reason for this stalling is the reactivity of some of these metal alkyls. So let's go over a little brief history. So Edward Franklin in 1848 did some early work with organo-zinc reagents. With the synthesis of diethyl zinc. This was a bit surprising at the time because as soon as water interacted with this reagent, it produced a very large blue flame coming out of the test tube, and it was quite exciting, I would assume. And you can still see this reactivity, of course, and it's one of the reasons why metal alkyls are a bit reactive or a bit elusive. They can be pyrophoric, which is when they interact with air or water, they have a tendency to start on fire. So care must be taken when you're handling these. Next, we have Victor Grignard, and he did work in about 1900 on the Grignard reagent, which is an organomagnesium reagent, which inserts a magnesium in between the a metal halide reagent. So a lot of times something with a bromine on it would make an excellent Grignard. Now, one of the reasons why he was successful is that he was very particular about keeping his glassware impeccably dry, and also the solvents. And as you may know from an organic chemistry class, and possibly preparing these in the lab, that these are very reactive to water, and you will not form a Grignard if there's any little bit of water in there. So it was very important that these reagents be kept away from water, and he earned a Nobel Prize for that work. Next, we have William Schlink and Carl Ziegler, and they both worked on organolithium reagents. So I'm going to write down organolithium reagents for both, starting in 1914 and then continuing work by Ziegler in 1930s. Ziegler also worked on aluminum reagents. In that time. So this is a little bit of the history, but we would really like to see what the transition metal elements can do. And with the exception of zinc, all of these are either in the first column or somewhere else on the chart. And for whatever reason, these were difficult to synthesize. And initially it was thought that the bond strength between a metal and an alkyl was just too weak. But Wilkinson came along and synthesized the hexa methyl tungsten complex. And it was relatively stable. It had quite a good bond dissociation energy, is based on some experiments that were run on it, and they found that the bonds between the metal and an alkyl are actually fairly strong. And that's a good sign for us to actually be able to prepare these. What it tells us is that thermodynamically it should be possible to make these, but perhaps kinetically it's difficult. But we can block kinetic pathways a lot easier than we can strengthen bonds, so that bodes well to making more reagents. Now, one of the reasons why we would like to make these reagents is for a completeness of reactivity, and something that the Grignard reagent really helped with. And you'll realize, or hopefully can think about, if we have a halide reagent, so some alkyl here with halide, we'll pick bromine. This R group right here is going to be partially positive because our bromine is going to take a little bit of the electron density away from the R, the carbons. And so we've had electropositive carbons available to us for quite a while. But one of the things that metal alkyls do is gives us access to R negative, which expands the reactivity that we can explore. So here's an example of R negative, partial negative. So now we have nucleophilic carbon. And we can use this to directly in reactions, or sometimes we can use these actually in organometallic reactions or catalyzed reactions as well. But having that R negative or negative carbon group is an important tool in the organic chemistry toolbox, whereas before we just had the positive portion. Now, why do metal alkyls fall apart, or what is one of the main degradation pathways? Well, a major problem is called beta hydride elimination. Now, one of the reasons why Wilkinson was able to synthesize this particular complex is it has no beta hydrogens. The methyl group is just alpha hydrogens. So what do we mean by a beta hydrogen? So I'm going to draw up here metal, and I'm going to draw the metal alkyl with an ethyl group. Ethyl groups will have beta hydrogens, so that's why I'm going to draw it. And I'm going to draw in the hydrogens, even though most of the time we don't do that. So here's the alpha carbon. That's the first carbon. Those would be alpha hydrogens. And then we have beta hydrogens here. Now I drew this one closer to the metal, and if it's in the same plane, so remember these bonds can rotate, so at some point it will end up in the same plane as this whole thing, so all in one flat area. And so it has to be in the same plane so that the same orbitals and everything can interact. And then the second thing is we have beta hydrides or hydrogens available, and if we have electrons on the metal that in an empty space, so it's not coordinatively saturated, and so yes, we'll have some other ligands on the metal, but say we have some space over here, right? What can happen is the electrons from this hydrogen can kind of go there, that can go there, and then we end up making a new complex with a hydrogen directly bound to the metal, and then we have an alkyl or an alkene complex right here. And what often will happen is this alkene will then fall off of the metal, because when we do this, we're going to add 2 electrons. So if we think about our electron counting, in this case we had an X ligand on the metal, but now when we go here we have an X ligand, the negatively charged hydrogen, and then we have an L ligand here, the alkene. So we've gone up by 2 electrons since we've added a neutral ligand to the metal. We keep 1 X ligand, that did not change. So this will not happen if the metal is already at 18 electrons, or if there's no space here for it, or if there's no hydrogens available for it, or if they can't get in the right orientation or all in the same plane for this concerted reaction to happen. We think that this all happens in one step. So it's important that that be lined up properly. All right, so ultimately this will end up doing this, probably. That plus the alkene. And a long time ago, it was difficult to have spectroscopy that would have been able to measure this, and so it was hard to know exactly what was happening. But once we figured out that beta hydride elimination is a major degradation pathway for metal alkyls, we were able to make stable metal alkyls that address these problems with the kinetics.